Okay, we'll go ahead and get started. Welcome everyone to today's sustainability seminar. I am Beth Mashesky and I help organize the Sustainable Seminar Series with Nancy Holm. I'll remind everyone here to turn off their cell phones. And then we'll be recording the seminars, so I will hold all questions till the end, at which time I will bring the microphone around so that people online can hear your questions. And then for people who are listening online, you can type in your questions at any time and we will answer those at the end as well. The seminar will be posted on our website within about a week, and then we also have archived about 10 years of seminars on our website. So I am very pleased today to welcome ISTC's very own John Scott. John is our senior analytical chemist, and he's been at ISTC since 2001. He holds a dual bachelor's degree in chemistry and environmental health from Illinois State University. His research interests include emerging contaminants, water quality, biofuels, bioproducts, and natural products. Please join me in welcoming John Scott.
Thank you all for coming. So unconventional sources of oil and gas are becoming increasingly important to meet the U.S. energy demands. In response to domestically sourced energy, unconventional extraction such as horizontal drilling and hydraulic fracturing of shales are in locations such as Pennsylvania, Texas, New Mexico, and North Dakota is a commonplace. So unconventional extraction of oil and gas has been a game changer for the United States. And over the next 15 to 20 years, these operations are projected to double. So it's very important. Hydraulic fracturing operations require large volumes of water. Depending on the formation, a typical well can require 2.3 to 5.6 million gallons of water. And in addition to that, there's many chemical additives that need to be added to these fracturing fluids. And these would include mineral acids, scale inhibitors, biocides, friction reducers, and acid inhibitors. Now, they only usually account for about 1.5% of the total volume of water. However, given the large volumes, we're talking about 35 to 70,000 gallons of chemical additives per well. The chemical additives utilized, they depend on the drilling operation, what type of energy is being extracted, and the formation. But here's a list of some that I took off the website Frac Focus. And you can see there's certain chemicals like xylene or naphthalene, and these are regulated because they're known to be toxic and carcinogenic. However, many of these compounds are not regulated by the U.S. Drinking Water Act. What's going on?
Sorry.
It's okay.
No, slide advancing.
Oh. Okay. So given the large volumes of water used and the chemical additives that are used and the oil-gas interaction, there's potential to be contamination there as well. So if we look at Pennsylvania for an example, here's complaints from 17 counties in Pennsylvania. And you can see about 1,300 of them are water related. In these counties, there's about 2,900 fracking pads. So that equates to about one complaint for every 2 fracking pads. So, and within Pennsylvania, there's actually been 271 confirmed cases of water degradation from hydraulic fracking operations. So why do we care about this in Illinois? So here's a map of known formations that contain shale gas. In the industry, they're referred to as plays. And if you look here, about 1/3 of the state of Illinois below us is a New Albany shale, which is projected to contain at least 86 to 160 trillion cubic feet of natural gas. So it's very relevant to Illinois. In anticipation of large-scale hydraulic fracturing in Illinois, the Public Act 0980022 was proposed in Springfield, and in June of 2013, the governor approved legislation requiring permitting of hydraulic fracturing. and they created SB 1715, which is called the Illinois Hydraulic Fracturing Regulatory Act. This SB 1715 is considered one of the most comprehensive fracking bills ever created. One component of this bill is that it requires comprehensive water monitoring before, during, and after fracking operations. So, given the complexity of the fluids associated with fracking, testing for contamination could prove to be very labor-intensive, very time-consuming, and very expensive. And here's a figure just showing some of the sample prep and instrument techniques to analyze for contaminants associated with these fluids. Now, this figure is far from complete, but it gives you an idea that this is a complex issue. So, there exists a need for an inexpensive, fast way to screen for contamination caused by fracking fluids. Okay, so molecular luminescence spectroscopy is a technique that utilizes the absorption and emissions of photons by a molecular species. Fluorescence is a subset of this phenomena, and it occurs at a very rapid rate, usually 10 to the -5 seconds. And also, the excitation-emission spectrum obtained is different for different molecular species. So creating fluorescence excitation-emission spectrum for different wavelengths is termed a excitation-emission matrix, and I'm going to call it EEM. And this is an example of a waterfall plot and a contour plot for a quinine sulfide solution. So the axis here is the excitation wavelength, the emission wavelength, and the z direction is the intensity of the emission at the specific wavelength. So it's the height of the peak. So this is a contour plot, same thing, except for in this case it's the color that represents the intensity. Blue is the least intensity. As we go from red to gray, the intensity is increasing. So all the data I'm going to show you in this presentation are going to be contours. They're much easier to look at, much easier to interpret. Let's see. So fluorescence. Let me show you an example of fluorescence. This is tonic water. It contains quinine. Your best safety glasses in case something goes horribly wrong. Can you see it glowing blue? So that's the fluorescence of quinine in this tonic solution. And Mike brought the gin so we can have cocktails after my talk. Okay, so in order to test our EEM fluorescence hypothesis, we first needed to collect oil field brines within Illinois that are near potential fracking targets within Illinois. And here is a table of the samples that we collected, and here's a map of where they came from. Let's see. So the sample types we collected were 6 produced waters from oil extraction sites. We also collected 5 groundwaters, 2 of them being by the first produced water we collected. Also, we collected 2 surface water samples near oil extraction sites. And luckily, we were also able to obtain a fracturing water from oil extraction process, and this is Quaranta number 6. This is an actual fracking water. And the operator indicated that when we collected the sample that the major chemicals used were a mineral acid and a gelling agent. So when we got the samples, they actually contained 2 phases, an oil phase and a water phase. So we brought them back in the lab, we just threw them in a separatory funnel, and we separated the 2 phases. And all the work that we've done was actually just the water phase. Okay? All right, so for the produced waters, we looked at things like pH, conductivity, elemental analysis, clean carbon, sulfur, nitrogen, major cations and anions, trace metals. For the fresh waters, we just pH, conductivity, carbon analysis, major cations and anions, and trace metals. And then what we did is we compared our produced waters and fracking waters, or fracking water, to what was reported in the literature for shale gas waters. And this is the reference that we used for our comparison. So also, we looked at polyaromatic hydrocarbons, PAHs. These are known to exist when there's oil-water interactions. They're a common contaminant of this type. They're basically just benzene rings all hooked together. We found PAHs in every produced water except for Stinson number 10. The PAHs were mostly the lower molecular weight ones. Nothing over 4 rings was detected, which makes sense because as you have larger ring systems, the water solubility definitely decreases. So the nice thing about PAHs is they fluoresce very nicely, so they can be used as a surrogate to determine contamination as well. So, and I'm always looking at PAHs, so a day without PAHs is like a day without sunshine for me, so we threw them in there too. Okay, so this is important. This is the dissolved organic carbon and dissolved inorganic carbon concentrations of all the waters collected in the study. And you can see the fresh waters are red and the produced waters are blue. And these plus signs are the literature values. So for the produced waters, the dissolved organic content, or dissolved organic carbon, I'm going to call it DOC from now on, and was about from 2.2 milligram per liter to 23 milligram per liter, with the blue sample being the highest of the produced waters. The fracking water, Quaranta, was actually about 68 milligrams per liter. And the fresh waters range from about 1 to 13. These two here were the groundwaters, Moweaqua and Assumption, and they were very low, less than 2. And the thing you can see here is that actually the shale gas waters in the literature are magnitudes higher in TOC, much, much greater. So that's going to become very important. You're going to see how this relation to DOC and fluorescence works together. So here are the concentrations of sodium, potassium, and rubidium in the samples collected in this study. And you can see our produced waters and our fracking water are about 1,000 times greater than our fresh waters. This is also where seawater is at, so there are a lot more sodium in our produced waters and fracking waters than seawater. As for potassium, it's about 100 times lower than the sodium, but still 100 times greater than our fresh waters. For rubidium, we didn't detect any in our fresh waters, and we're still about another, 100 times lower than potassium. The literature values for potassium were much higher for potassium. I mean, the literature values for the shale gas waters are much higher for potassium and rubidium. So that's what I want to say about the cations. Okay, let's see here. Anions. There was no literature values for anions, but chloride, very high in our produced waters versus fresh waters. And same thing with bromide and iodine, sulfate. You can see where seawater would be for chloride. So the bottom line is that the chloride, bromine, and iodine concentrations in the fresh waters were 2 or 3 orders of magnitude lower than the produced waters. Okay. So overall, the fracking waters used and the produced waters used in the study are much more salty than those in the reference for shale gas waters. And this is also seen in the conductivity. Conductivity of seawater is about 50 millisiemens per centimeter. Fresh water is about 0.1 to 1.0. So these are definitely more salty than the reference values. And it's just basically what we've seen here with our produced waters, that a little bit of contamination can seriously contaminate it, or a little bit of infiltration of these into fresh waters can cause some serious contamination. Okay, so in addition to the quantitative information, we also screened our PAH extracts for, by GCMS. And this is not an exact science, however, it can give somebody a good feel of what types of classes of compounds are present. And one of the things that we found, this is the fracking water extract, GCMS chromatogram, and one of the things we found was 2-butoxyethanol, which is a fracking fluid stabilizer, and it's one of the most common fracking additives out there. But unfortunately, it doesn't fluoresce. So, but we found it in our fracking water. Also, we have this compound called Bayer 28589. It's a nitrophenol. It's typically used as a lubricant, or I'm sorry, an antioxidant in drilling fluids. So it makes sense that we've seen that here. And also, this is bis-2-ethyl hexyl phthalate. Very big peak here at 22 minutes. Those are also phthalates are also commonly associated with drilling fluids, and they're also used as breakers. In our reference that I showed you earlier for the cations, they also found a lot of phthalates in their fracking fluids as well. So no surprise there. Also, we found many substituted phenols, substituted quinolines, isoquinolines, and naphthalines. So these are all aromatic in nature, and they all should respond to fluorescence. So that's the bottom line here. Okay, so the instrument that we used to perform the fluorescence measurements was a Horiba Aqualog scanning photometer scanning spectrophotometer. fluorometer. And the instrument is unique in that it does absorption and fluorescent emission measurements simultaneously. We scanned excitation wavelengths from 240 nanometers to 700 nanometers, and then we collected the emission wavelengths from 240 to 800 nanometers. We set the integration time for 0.1 second, and under these conditions, it took us about a minute to analyze the sample. So it's fracking fast. Let's see, also we analyzed DI water and then subtracted it from all our sample results. Okay, so interfiltering effects are due to the sample absorbing light in the excitation mode and absorbing light in the emission mode. And this is termed primary and secondary filtering. So since we're able to collect absorption measurements simultaneously, we're able to correct for these interfilter effects. And that's one of the first things we do after we collect the EEM data, is we correct for interfilter effects. The other thing is Rayleigh scattering and Raman effects are due to the scattering of light by particles smaller than the wavelength, the radiation of interest. Now Raman scattering we can get rid of by blank subtraction. However, Rayleigh we cannot. So there's a post-processing method where you basically remove the first and second order Rayleigh scattering. Software just puts zeros for the intensities in there. The last thing we have to do is we have to normalize the data to something we call a QSU unit, quinine sulfide unit. And what we do is we analyze a 1 milligram per liter quinine sulfide standard before we run the samples, and then we adjust the results that we get for every sample according to what we got for that quinine sulfide standard. And the reason why we do that is so you can compare the data from one instrument to the next. So it normalizes it so we can compare it. Okay, so here are the EEM contours of the 5 groundwaters collected in this study. And natural organic matter, including fulvic and humic acid, typically represents the vast majority of TOC in a sample. And it also is responsible for the background fluorescence of the sample. These EEMs that we're getting here are typical for natural waters. And however, you notice there's a big scaling difference here. These two top ones, very, very low intensity, you can barely see it, but the McLean groundwater wells are much more intense. And you can see here that the TOC is higher in these samples. So there's definitely a relationship between TOC and the strength of fluorescence. And these TOCs are about less than 2. These two are right around 5, and this is at the upper end, about 9.3. So I think that's pretty high for groundwater. It's getting up there. So here are 2 EEM contours of surface waters. They were actually the highest in TOC of the fresh waters, but their fluorescence signals are similar to the groundwaters, but they're less intense. So either there's carbon in there that doesn't respond to fluorescence, or the carbon that's in there responds to fluorescence less than the carbon that's in groundwaters. Okay, so here are EEMs for 4 of the produced waters, and you can see that the excitation emission wavelengths have shifted down lower. So you can see that there is a common peak to these 4. It's at about 240 excitation, 356 emission. However, there are other secondary peaks down here in this region that are different depending on which produced water you have. Let's see here. Blue number 6 was actually the most intense of all the produced waters that we obtained, and it also had the highest TOC. Here's 2 more contours of produced wells, as well as our fracking water, Quaranta. This was the most intense of all the fluorescence samples that we analyzed. You can see there's a very strong peak here at about 275, 300. The Reinert-Bannert was actually the least intense of all the produced waters. Now, in addition to the produced waters, we obtained an anti-corrosion agent from an operator at one of the sampling sites. And I love this example. This is a great example of interfiltering effects. So contour A here is the anti-corrosion agent analyzed neat. And you can see it's extremely intense fluorescence signal. However, the signal is kind of distorted. It kind of looks like an upside-down Pac-Man. So the reason for this distortion is right here. This is the absorption spectra for the sample. And you can see here the transmittance below 300 nanometers is pretty much 0. So no light is getting through to excite what's in the sample. So what you do in this case is you have to dilute your sample in DI water. So we dilute our sample 100-fold. Here's the absorption graph at 100-fold dilution. You can see about 80% now is making it through those lower wavelengths. So we get a much nicer EEM contour. The peak is more defined, and we can find the maximum of it. So this is a great example of interfiltering effect. Okay. In addition to the anti-corrosion agent, we obtained 11 common fracking biocides. These are the 11 that we looked at along with their CAS numbers, and they gave them abbreviations because I'll slaughter these names if I try to say them over and over. Out of the 11, 4 of them actually respond to fluorescence. So that's these 4 here. Now, of the other ones that do not respond, there is tricks you can do. You can chemically react them with something that causes them to fluoresce. We call it derivatization. However, that's beyond the scope of the study. We didn't really have time and the effort to go do it, but that's something we could do later on down the road if we needed to make those respond to this instrument. Okay, let's talk about fluorescence ratios. It's usually used at? That I don't know. It does seem pretty high, and we wanted to start somewhere so we can at least see if they respond. But the problem with fracking fluids is companies don't like to disclose what's in them and how much. And yeah, I mean, that's a good question. Sure. Yeah, absolutely. Yeah. Okay, so let's talk about fluorescence ratios. And certain features of a fluorescence EEM is related to the properties of dissolved organic matter. For instance, fluorescence indice FI is actually evaluated right here. I think it's 370 nanometers. You take this spot, divide it by this spot, and a value of about 1.4 indicates is typical for terrestrial dissolved organic matter, stuff that you would expect to be leaching from soil. And a value of a 1.9 is usually dissolved organic matter that's been created in situ, like from algae and bacteria. And also people have found as you lower the, as the FI goes lower, the aeromicity of that sample increases as well. Also you have a biological indice. It's right here, these 2 points. If you get a value of 0.8 to about 1.0, it's biologically produced dissolved organic matter. Less than 0.6 is usually considered recalcitrant dissolved organic matter. And the other one is humification index. We integrate the areas here and here, and less than 5 is usually pretty fresh dissolved organic matter, and from 10 to 30 is usually considered aged dissolved organic matter. So we looked at these indices for our samples, and the groundwaters are about 1.4, which is typical for aged dissolved organic matter. The surface water is about 1.3, is what you would expect for, is in the range of many fresh waters. However, the values for the produced waters were overall much lower. They did not overlap with the groundwaters at all, and this would suggest that these there's an increase in aeromicity here. Now we also had some GCMS scan data that indicated there's a lot of aromatic compounds in these samples as well. So this kind of correlates nicely with what we would expect with fluorescence indices. As for the biological indices, the groundwater, surface water, and fracking waters are all in the narrow range of about 0.7 to 0.9. The produced waters, on the other hand, ranged all the way from 0.4 to 2.2. The Stinson and Reinert-Bannert samples were up here, and the Timon was down here. What this means, we really don't know right now. However, it's something that could be interesting that we should, that warrants further investigation. So, the humification indices. Let's see, the fresh waters all had relatively high. This is about what you expect for typical thing for aged dissolved organic matter, which is expected given the long hydraulic residence time in these aquifers. The fresh waters here, the surface waters, are in the right range, what you expect for a stream. It's consistent with, the stream sampled in here. We estimate them to be less than a year. And all the produced waters and the fracking waters were very low in the humification indices. And let's see here. Come on. Well, anyhow, they were much lower. So we have to be careful about interpreting these low HIX values, and the reason for being is that to calculate these, you need a peak here in this range. And here are some of the produced waters and the fracking water, and you can see there's really no intense peak in that area. So to infer anything from these humification indices of the produced waters is probably inappropriate. So in addition to the fluorescence spectrum, you can also interpret, there's a lot of relationships with the absorption spectra in the properties of dissolved organic matter. Here are the, on the right, you have the produced water absorption spectrums, and here are the freshwater absorption spectrums. You can see the fracking water absorbs light the greatest. However, it could be due to the chemical additives used. Also, you notice that as you go below 300 nanometers, the slopes of these guys drastically increase. As for the freshwaters, they are more gradual increase in their slopes. So the absorption spectrums are very different. SUVA 258 is a specific absorbance of light at 250 nanometers, or 254 nanometers, divided by the dissolved organic carbon. It's correlated with the aeromicity of dissolved organic matter, and this has been verified by NMR, carbon-13 NMR. And here are the SUVA 254 values for our water samples. You can see that the groundwaters and surface waters, they overlap between about 4 and 6, and all the produced waters are lower between 1 and 3, and the fracking water is very high up here at 9. So this, let's see, this guy here, it could be due to the chemical additives absorbing light, but also it would indicate a higher degree of aeromicity in the sample. And it correlates well with the FI ratio, and it correlates well with what we see in GCMS data. There's higher aeromicity here. However, these guys are lower, and they are inconsistent with the fluorescent indices that we calculated. So we don't know why there's that inconsistency there with SUVA 254. Okay, spectral slopes. Previous work has tied these spectral slopes to dissolved organic matter molecular weight. So you take the slope of the absorbance spectrum from 275 to 295, and you divide it by the slope at 250 to 350. And you can see here, these freshwaters are generally lower than the produced waters. There is some overlap, but this would suggest that the produced waters have a lower molecular weight. So this is low molecular weight over high molecular weight. However, you would have to do further work to verify this, like size exclusion chromatography and so on. Okay, so we acknowledge that all the interpretation of fluorescence indices and SUVA 254 and spectral slope ratios, this has all been developed on natural organic matter, okay? And it's all been done on surface waters and very shallow water reservoirs. How this relates to deep field oil brines, we don't know. But certainly it warrants further investigation. Taking our data and coupling it with size exclusion chromatography, NMR, biological and biomarker assays could really prove to give us some fruitful information. And this could be something that could be utilized by well operators to help them characterize their produced waters while they're running. So definitely lots of work left to be done there. Okay, so now that we've covered characterization of our samples in the fullest extent, now let's answer ourselves the question, can we determine contamination by fluorescence spectroscopy? In order to do this, the first thing we need to do is to select 3 excitation-emission wavelengths for each produced water. And in this fracking water, we would take here, we would take one here, and we would take one here. So those are the 3 wavelengths that we would look at. And this term, and this method of peak picking is what it's called, when you just pick out the most intense spots. So that's the name for it. So next, we have to estimate the minimum detectable contamination level. It's necessary to determine when the fluorescence signal is significantly higher than the background. So therefore, the minimal detectable dilution of a produced water in a fresh water is estimated as 3 times the standard deviation of the freshwater fluorescence divided by the fluorescence at the peak of the produced water. So in an example, let's consider the Moweaqua diluted with the blue sample. Okay, and that's what this example is here. So we find the linear background by taking the standard deviation 4 wavelengths before and after our peak wavelength, and that's how we get our standard deviation. And we create, that's what this linear background is here. And we go up 3 standard deviations, and that's what we have to be above to say that we can detect it. So for the freshwater samples, we lump them into 2 categories, low TOC and high TOC. So here are the minimal detection limits for the low TOC samples. And you can see for the blue and the fracking water, they're actually down to about 1% and lower. Okay? For the high TOC waters, big difference. You can see that these minimum detectable concentrations are extremely elevated. And in some cases, we could not even detect them, and that's what these dashes are here. So, to answer the question, can we use fluorescence to detect contamination from fracking fluids? The answer is yes. However, it depends on the TOC and the background fluorescence of the fresh water in question. So that has a major effect on how low we can go. So, as an attempt to lower our detection limits, the first thing we did is we explored something called integration time. Integration time is the interval that the instrument will measure the fluorescence. And theoretically, the signal to noise is proportional to the square root of the integration time. So a very simple equation. So going from 1 second to 2 seconds is theoretically should increase our sensitivity by about 41%. Okay? So when we analyze with 0.1 integration second time, it took us about a minute to analyze the sample. But if we go to 5-second integration time, and that's the maximum we can do on our instrument, we go to a 10-minute analysis time. So you're increasing your analysis time by a factor of 10. So which is still pretty fast. So what we did is we looked at the Stinson produced water, and we took the worst case scenario, well 14, the highest TOC, fresh water, and we took Moweaqua, the lowest TOC, the best scenario. And we calculated, and we ran, excuse me, we ran these samples with a 0.1 second, 1 second, 2 second, 5-second integration time. And when we do that, we don't get much for well 14. And the reason for it is because the produced water signals and the background signals are both going up at the same time. So it's basically having a null effect. However, when we look at the low TOC sample, actually at 1 and 2 second integration time, we're getting down to about 3 to 11-fold sensitivity. So it's really increasing, it is increasing the sensitivity for these low TOC samples, and it helps. And at 5 seconds, it pretty much has no effect. So we optimized it about 2 for this mixed combination. Okay, the next thing to do in an attempt to resolve these signals from the produced waters and the fracking water from the high TOC waters is we looked at something called decomposition models. Okay? So these decomposition models have been demonstrated in the past to be a useful tool in characterizing dissolved organic matter. Parallel factor analysis, PARAFAC, is a computational method that decomposes EEM spectra, and it basically breaks into a set of trilinear terms in a residual array. So PARAFAC can remove a great deal of the complexity of these three-dimensional spectrums, and it can resolve overlapping excitation-emission peaks. Okay, and the things that you get out of this is the most probable number of components that fluoresce. You also get the EEM spectrums of those components, and it also gives you relative concentrations. So what I did is I create PARAFAC models for all these produced waters in the fracking water. I did that. We did that with data from spiking. So each produced water was spiked into each fresh water at 0.1, 1, 10, 20, and 50% concentration. Let's see, the model software I used was Eigenvector Solo Mia, and I explored each model with 1 to 8 individual components. So here's an example of the output from the model. And one of the things that you do is you want to maximize this percent explained. And what this means is for all the fluorescent signals in your model, how much of it can this model take an account for? So you want to maximize this. The other thing you want to maximize is what's called the core consistency. You need to have a value greater than 0, and 100% is considered the best. So those are the two things you want to maximize with these models as you try to determine how many components are best fit. The other thing we have to look is called the residuals. And for here, we want to make sure that these bars are less than these. We want to have the least amount of bars above these red and green lines. And the other thing here, this is the other residual that you need to look at. You need to look at this for each individual sample. Now, basically, this is the real data subtracted from the model data. So what you want to see here is no chemical information. You just want noise. Okay, and this is an example of a bad residual. There's a lot of signal there, so you wouldn't want that. So anyways, I went and did this through all the models I created, or all the sample types. And afterwards, once you get a model that you think is really, really good, what you do is called split hat validation, and that basically tells you how robust your model is. What that does is split the data set in half multiple times, creates a model, compares them to each other, and gives you what's called a similarity measure. So 100% is considered the best. So that's just to give you a feel about what PARAFAC modeling is. Of all the models I created for the study, there was only 2 that were successful. It was the Quaranta 6 fracking water, and it was the Bilyeu 6 produced water. So the first output from PARAFAC, like I said, is the individual components. So for the fracking water, the best fit was 3 components. This first component is about what you would expect for natural organic matter. It looks a lot like the groundwaters and the surface waters that we looked at earlier. Component 2 and 3 is due to the fracking water. Okay. It's also interesting to note that here, if you would look at just the EEM of the fracking water, you wouldn't see this peak here. However, PARAFAC was able to pull it out. So here you can see the importance of PARAFAC as opposed to peak picking. So the other output is the loading. This is related to the concentrations of each component. This is component 2 in the fracking water model. And you can see here are the backgrounds. This is the well samples with no spiking. And this sawtooth pattern is about what we would expect for a model for spikes. This is 0.1% spike, 1%, 10, 20, 50. So that's good. That's what you want to see in your model. And this is very encouraging because 0.1% is much higher than the background. However, what we really need to do is go back and run this handful more times, get a standard deviation, and then you would be able to give you an estimated level of detection. So encouraging. It looks like it's working for this one. This is component 3 of the same model. However, the slopes are they're still that sawtooth pattern, but it's not as pronounced. This component is probably less sensitive, or it's less abundant in the produced water, or in the fracking water. For the blue model, there was only 1 component that was responsible from this produced water. However, the interesting thing here is this is a surface water, and you can see the slope is a lot less than these groundwaters. So there's an effect called quenching. So if there's inorganic and organic compounds in the sample matrix that can potentially reduce your signal of fluorescence. So this would suggest that since these, as each step of the spikes go up, you have less signal. There could be quenching going on here. However, we'd have to look further into that. Okay, so the last thing is since the anti-corrosion agent and the biocides responded to fluorescence, we looked at the minimum detectable concentration of these biocides and agent in our waters. We took the low TOC groundwater and the high TOC surface and groundwater. And you can see anti-corrosion agent, we can see about 1% in the low TOC. But in the higher TOC samples, 6% and 10%. That's how much you can detect. For the biocides DDAC, DMOL, and TBPC, we cannot detect them at all in the higher TOC surface water and groundwater. But for the low TOC groundwater, we can see about 72 to about 300 milligram per liter of these biocides. Biocide DBCA, we can see it in everything. However, in the high TOC surface water and well, it's from about 450 to 600 milligrams per liter. And in the low TOC, about 12 milligrams per liter. So we can get pretty low for that biocide in a low TOC sample. Okay, so summary, we looked at 1 fracking water, 6 produced waters, and 5 ground waters. And 2 surface waters. They were collected and utilized to demonstrate the ability of fluorescence spectroscopy to detect contamination from oil extraction operations. The fracking water and the produced waters in the study were chemically much different from what we've seen in the literature, especially with regards to dissolved organic carbon and much higher in salt content. So we have successfully demonstrated it as a screening tool. However, the limit of detection is definitely influenced by the dissolved organic carbon and the background fluorescence in the freshwater samples. Basically, the samples we used in the study were the most conservative that you could find. They were low TOC, high salt content. So we would expect this to respond better to shale gas waters and those types of materials. Optimization and integration time was able to lower the detection limit. However, it was only for low TOC, low background samples. PARAFAC was actually successful at decomposing these signals from the produced waters and the background fluorescence in fresh waters. However, it only worked for those produced waters and fracking waters that were most intense for fluorescence. We also, anticorrosion agent for common biocides were achieved at relatively low concentrations for TOC waters, but just like everything else, for the high TOC, they were hindered by the background. I'd like to thank the Prairie Research Institute for funding of this program through the for this project through MRAP program. I'd like to thank Lois Yokosula for her contributions at the beginning of the proposal and for writing the proposal, helping us write it, and the input during the project. Susan, Olivia, and Raul for all the chemical analysis. We'd like to thank the Stewart producers, Howard Energy, Sharp Energy at Nichols for providing our produced waters and our fracking water. Louis Jordan and Robert Altoff for their assistance in getting the groundwater samples, and of course Beth and Nancy for, I guess, this invitation to present and for the report that they're going to soon review. And also they're going to put this report up on the ISTC website along with our other technical reports. So given all this, before I stop, I just want to show you a couple other applications since we've started this project that we found. One of them is a project with bioengineering group on campus, DuPont and Pan. They have a nanoparticle that they have designed to treat oil spills. So we use this fluorescence method to determine if they're removing the aromatics that are associated with an oil spill. And this is their first stab at it. And you can see here the blue line's contaminated seawater and the red line's treated contaminated seawater. So there's not much difference. It's not really removing the aromatics. So they took this information, they went back and they changed their nanoparticle. And now we can see that here's the petroleum spill, the blue on top. And here's the treated petroleum spill, the nanoparticle, and we're starting to see a reduction in fluorescence. So it's helping them, is a tool for them to help them determine where to go with engineering their bioparticle, or their nanoparticle. And this is funded through IC, the Institute of Sustainable Energy and Environment. Okay, so military, you got to have a military application. So over the next 10 years, the military wants to get rid of all the TNT, and they want to replace it with something called IMX 101. So these insensitive munitions, they call them, they have the potential to find their way in the environment at training sites or where they test these things. So there was a proposal to look for these compounds in this IMX 101. So they respond nicely to fluorescence. We spiked them into a surface water. We were able to see them there at about half of a ppm. This was part of a proposal to Ceradip. It wasn't funded, but actually this component of it was very well liked. So maybe we can repurpose it and resubmit it if the opportunity presents itself. This is also, we could also use this technique to evaluate treatment of pharmaceuticals and personal care products. Rupa and Kishore have been working with ibuprofen, which also fluoresces very nicely. This is a calibration curve that we've created. We can see it in DI water down to about 20 parts per billion. So this is an example of an experiment they ran at different times and different treatments, and you can see it's reducing the ibuprofen. So it's a quick way to measure and provide feedback to them. The other thing is carbon capture. This is ISTC, and we're really into carbon capture now. So one of the things in carbon capture is they use these amine-based solvents. MEA is one of the more common ones. So one of the difficulties they have is having a hard time measure the MEA CO2 complex. So this is an example of monoethylamine, 3,000 ppm with no CO2 loading. And then after they loaded it with CO2 and let it sit for a day, they gave us the sample. And it was so intense in fluorescence that we actually had to dilute it tenfold. So we have to do more investigating, but this is quite exciting for us because this could be a way to measure carbon loading in these solvents. So if you have an idea, an application, let us know. We'd love to try it out. And thanks for listening. Questions?
Great presentation, John. We'll take questions from the audience now.
Nobody. Yes, Mike.
So it takes you 5 minutes to collect the spectra. All that analysis you have to do, what's the time on that? I mean,
The data analysis. Well, the post-processing actually only takes several minutes. Is that about right, Olivia? Yeah, because that's built into the software. But yeah, for the modeling, and if you want to model the data, yeah, there is a lot. There's something involved there. But any technique, if it's GC, you're going to spend even more time going through peaks. So there is some aftermath time that you would need to do, but it's comparable to everything else. Data interpretation, I guess. Yeah. Yeah.
You want to say a bit about how much data you need for a proper model?
Oh, for a PARAFAC model? Yeah, it could be hundreds of samples. The more data, the more samples you have, the better these models are. Now, a lot of these models that I created were only about 40 or 50 samples at the most, but typically you load these things up with hundreds of samples. So yeah, it would be cool if we could sample all the groundwaters in Illinois and run them and create this giant model, and then use that to compare sites with, I guess. But
even with the 40 sample model, some produced waters can pick out low levels of the
yes.
verify.
Yes.
So the more data, the better. Presumably, be able to get down to the low.
Yes, like for those produced waters that we did, when we did not get successful models, yes, if I had more samples, I may have gotten, I may have gotten better models. Absolutely. Yes?
So the fracking fluids vary, I imagine, in their chemical composition.
Oh, tremendously.
I suppose some of them are rather low in fluorescing material, some of them are really high in
Yes.
monocyclic hydrocarbons, squills, and liquid ones, and so on.
Yes. Yeah, extremely complicated and change from site to site. Yeah, definitely. And just because something has a high TOC doesn't mean it's going to fluoresce. An example is methanol. A lot of these fracking operations use large amounts of methanol, and you could have hundreds of thousands of TOC with methanol, and it won't even respond to fluorescence. In fact, it'll quench fluorescence. So, yes, Kathleen.
Does the Illinois fracking law require disclosure of fracking fluids?
Yes, but there's ways that the companies can get around that, called the Halliburton loophole. So if it's proprietary and it's their special sauce and it gives them a competitive advantage over another drilling operation, then they can usually get around it. But if you read the law, and actually it's sitting next to my bedstand, it really helps me go to sleep at night. But they do mention something about that they have to disclose. But they can get around it sometimes by using that Halliburton loophole. So absolutely. Anybody else? No? Okay. Well, thank you
Thanks,
for listening.
John.